Hi everyone, let's continue. So we call the Trebuchet's theorem. Okay, so we call the Trebuchet's theorem, we have if the probability of x far away from the mean is small, right? If, let me draw the picture here. Okay, so it's like that. We have mu in the middle, and this is mu minus k sigma. This is mu plus k sigma. So we have the probability of x far away from mu is small, right? And we have the probability of x near mu is big. Okay, so this is this one, right? The probability of x far away from the mean is small. How small? Less than equal to 1 over k squared. Okay, now if we substitute x bar for x, and we substitute sigma over square root of n for sigma, okay? Because we know x bar, the sample mean, is a random variable, so we can replace x by the random variable x bar. And then the standard deviation for the sample mean is going to be sigma over square root of n, okay? So that's why here we get x bar and sigma, we replace sigma by sigma over square root of n. So this is what we get. And so the probability of the sample mean far away from, because it's the mean of the sample mean is the same as population mean, so we still have mu here, that the probability of x bar far away from the mean is small, okay? And we also have the other form, the population of the sample mean near the population mean is, the probability is large, okay? So those are two forms. So now let epsilon be k sigma over square root of n, okay? So now what happened? So sigma equals to k, epsilon equals to k sigma over square root of n. So you replace this by epsilon. Then what is k? Well, k is then epsilon times square root of n over sigma. So 1 over k squared. So 1 over k squared is actually epsilon squared. This is sigma squared over n, because square root of n times square, it equals to n. And then we have the sigma squared. Okay, so that's why when n goes to infinity, this guy goes to 0. So that's why we have the probability goes to 1. So far, so good, everybody? Okay, what does that mean? It means that the probability, the sample mean close to population mean, is so large. It's actually goes to 1, okay? So the sample mean is close to the population mean with high probability if the sample size is larger. So this is actually the theorem of the law of large numbers, okay? We use LLN to denote law of large numbers. So it's actually one of the important theorems in our course. So we have two important theorems, the law of large numbers and the central limit theorem. Okay? All right, so let's continue. So the theorem tells us that let x1, x2, x sub n be independent random variable, each having the same mean and variance sigma squared. Then given any epsilons greater than 0, the probability of sample mean close to the probability of sample mean far away from the population mean goes to 0. So the probability is small. And the probability of the sample mean near the population mean is very large, okay? So this actually tells us that sample mean approximates the population mean if n is large. Okay, so this is what it tells us. Okay, so let's use the theorem to look at example 4. In an experiment, an event A has the probability P of occurring. Suppose the experiment is repeated n times and the trials are independent. Show that the relative frequency of A, which is the number of times A occurs in n trials over the total number of trials, which is n, becomes arbitrarily close to P with arbitrarily high probability as n goes to infinity. Okay, so how do we solve this problem? Well, first we're going to define our random variables. So let me see here. So let's define n random variables. Okay, x1, x2, x of n, where xi equals to 1 if A occur in the I trial. Okay, and we define xi is 0 otherwise. So sometimes we call this xi is like a indicator random variable, okay, because it indicates whether A occurs or not. So this is an indicator random variable. So it indicates whether A occurs or not. And we can notice that, okay, because all the trials are independent, then we have the xi's. So the xi's are independent. And because they have the same distribution, so we say they are identically distributed. Okay, with the mean mu, okay, which is P, and the variance sigma square equals to P times 1 minus P. Why is that? Because all of these xi's, they are Bernoulli distribution. Okay, so all of the xi's, they are Bernoulli distribution. Well, the Bernoulli distribution is we have one trial is either success or failure. Okay, so that's why you can it's like a special case of a binomial distribution where your n is just 1. So the mean for Bernoulli distribution is n times p. Well, n is 1, so it's just p, and the variance is n times p times 1 minus p because n is 1. So the variance is p times 1 minus p. Okay. And then we have x1 plus x2 plus plus x of n. This is actually the number of times A occur. A occurs in the n trials. Okay. So that's why if we divide it by n, okay, so the sample mean is actually we add them all up and divide it by n. Okay, then this is gonna be the number of times of A occur in n trials over n. So this is actually the relative frequency of A. Okay, almost there. We know that by law of large number, the probability of sample mean minus population mean, which is P, okay, this guy less than epsilon goes to 1. So the probability of sample mean near the population mean is so large. How large? Goes to 1 as n goes to infinity. So this is what it means. Like show that the relative frequency, which is x bar, become arbitrarily close to P with arbitrarily high probability as n goes to infinity. So this is exactly what we have shown. So far, so good. So this example is similar like our weather report. So 40 under the same weather conditions, 40% of chance it will rain. So you actually record like how many times it actually rains under the same weather condition. Okay, so that's the relative frequency. Okay, let's continue. All right, so next topic. Suppose we have x1, x2, x sub n. They are independent and identically distributed. So identically distributed means they have the same distribution, probability distribution. So they're picking from the same population. Okay, so that's why people sometimes call this is IID. IID stands for independent and identically distributed. Okay, so suppose they are IID random variables with mean mu and the variance sigma square. Then the standardized sample mean is, well, we know the sample mean is x bar. Well, what's the standardized sample mean? Well, if you can remember, we have the normal distribution. Okay, so let me put it here. So the feelings like we call for normal distribution x, well, z is you use it to subtract the mean and over sigma. So this is the standard normal distribution, right? So how do you standardize a random variable? You use that random variable minus its mean over the standard deviation, and that's the standardized random variable. Okay, so the standardized sample mean is you use the mean, subtract the mean of the sample mean, and divided by the standard deviation of the sample mean. Well, the mean of the sample mean is the population mean. The standard deviation of the sample mean is the population standard deviation over the square root of n. So far, so good, everybody? So this guy is the standardized sample mean. All right, so that is why for individual values, such as like the normal distribution and the standardized, so standard normal distribution is going to be x minus mu over sigma. But now for sample means, the standardized sample mean is the sample mean minus mu over sigma over square root of n. So compare, you have an extra term here. Okay, so don't forget that. Right, next, let's talk about another important theorem of our course, the central limits theorem. Okay, so we have two important theorems, law of large number and the central limits theorem. So law of large number tells us that sample mean approximates population means. So how about the central limits theorem? Okay, suppose x1, x2, x sub n, they are IID, so they are independent and identically distributed with mean mu and variance sigma squared. So suppose we know the sigma, so suppose sigma is less than infinity. Then the standardized sample mean is going to be a random variable whose distribution function approaches to that approach to the distribution function of the standard normal distribution when n is large. That's why we also call it z, because z later on we show that it approaches the standard normal distribution. Okay? So what does that mean? What does that mean by saying the distribution functions approaches to the distribution function of the standard normal distribution? Well, suppose we look at the cumulative distribution functions of the standardized sample mean. So let's say f sub n of x are the CDF of the standardized sample mean, and capital F of x is the CDF of the standard normal distribution. Then this theorem tells us that for each values of x, when n goes to infinity, f sub n of x will converge to f of x. Okay, so that's why this theorem tells us that the sample mean is approximately normal. Okay, the sample mean is approximately normal when n is large. Okay, everybody? Okay, so let's see how we compute the example using this theorem. Example 5. If a 1 gallon can of paint covers on the average 513.3 square feet with a standard deviation of 31.5 square feet. What is the probability that the sample mean area covered by a sample of 40 of these 1 gallon cans will be anywhere from 510 to 520 square feet? So let's identify the numbers. So 1 gallon can of paint on the average. So this is the population mean with a standard deviation of 31.5. Okay, so this is standard deviation, right? What is the probability that the sample mean area covers? So a sample mean of a sample of 40 such 1 gallon cans can be anywhere from, so we're asking 510. So far so good, everybody. So here because we are doing like the normal distribution, it's a continuous random variable, so that's why the endpoint does not matter. Okay, so what is that? So because we know by the central limits theorem, we know that our standardized sample mean is approximately normal, right? It approaches to the standard normal distribution when n large. Okay, so when n is large. Okay, so let's see. Let's figure out what's that. Okay, so how do we change to the standardized sample mean? We subtract mu, so everybody subtract mu over sigma 31.5 over square root of n. Square root of n is 40. Okay, less than, so we do the same thing to x bar. Okay, so we do the same thing for 520. So 520 minus 513.3 all over 31.5 over square root of 40. So far so good, everybody? Okay, so let's plot this in our calculator. So we know this guy is z. Okay, so we plot this in our calculator. On the left, I have, okay, So everybody please pause the video here and let's plug in our calculator together. Okay, and I have 510 minus 5, 13.3 divided by 31.5 and then divided by, so it's the same as multiply by square root of 40. I get negative 0.6625, so we can round to 0.66. So remember, for the CDF values for the standard normal distribution, the Z values only 2 decimal places, where the probabilities are 4 decimal places. Okay, so here we keep 2 decimal places is enough. And the other one, we don't need to type it again, so just go up to your previous formula in your calculator. We place 510 to by 520, and then I got 1.345. So we actually round up. Okay, we get 1.345, so we round up to 1.35. Okay, so don't forget, if your next digit is greater or equal to 5, you actually round up. Okay, so let's see. So this is the same as, because we know it has the standard normal distribution, approximately by the standard normal distribution. So this is the CDF of 1.35 minus the CDF of negative 0.66. Okay, so let's find those numbers in our table. So where is our table? Right here. So 1.35, where's 1.35? Oh, next page. 1.35, this one. So 0.9115. Minus, okay, minus what? Phi of negative 0.66. So negative 0.66, negative 0.66, where is 6? Okay, here. So, which is this number, right? So 0.2546. 0.2546. Okay, plot this in our calculator. What do we get? I get 0.6569. Do you have the same answer? So this is the probability of our sample mean area covered by those 1 gallon cans between 510 and 520. Okay? Alright, so let's continue with example 6. So I really hope that you can pause the video and try to work on the problem by yourself first. Okay, so are you done? Let's check our work. Scores on the Stanford Binet IQ test are normally distributed with mean is 100 and sigma equals to 16. Part A, compute the probability that a randomly selected individual has an IQ greater than 108. Part B, compute the probability that a random sample of 20 people results in a sample mean greater than 108. Okay, so you can see the difference between part A and part B. Part A, we just randomly select individual, one person. Okay, so one person, because the distribution, see here, normally distributed means we have a normal distribution. Okay, so part A, we have the normal distribution. Okay, with mean is 100, sigma, standard deviation is 16. Okay, so we're looking for the probability of X greater than 108. Okay, what is that? Well, we know that if we have a normal distribution, we need to convert it to the standard normal distribution. The standard normal distribution is x minus mu over sigma. Okay, so 108 minus mu is 100 over sigma is 16. Okay, so this is z. And then 108 minus 100 is 8 over 16. Oh, that's 1/2. So 0.5. Greater than is the same as 1 minus probability z less than equal to 0.5, right? So here, for continuous random variable, less than equal doesn't matter. Okay, less than equal or less than doesn't, they're the same. The endpoint does not matter. Okay, so what is that? We have, this is the CDF of 0.5. So let's find the number in our table. So where's our table? Here, 0.5. Oh, next page. So 0.50. So 0.6915. So 0.6915. Okay, put this in your calculator, and what do you get? I get 0.3085. Do you have the same answer? Yay! Okay, let's look at part B. So part A is we just pick one individual, one person. Okay, and part B, compute the probability that a random sample of 20 people. So we have 20 people. So we have a sample. Okay, so a sample is 20 and is 20. Okay, so compute the probability of a random sample of 20 people results in a sample mean greater than 108. Okay, so here, what is the standardized sample mean? X bar minus mu over sigma over square root of n. So keep in mind that you have the extra term square root of n. Okay? Yeah, so compare this guy and this guy, the extra square of n over there. Okay, now let's continue. So the probability of x greater than 108, okay, is probability x bar, this is sample mean, so we minus mu over sigma over square root of n, and we do the same thing to the 108. Minus mu 100 sigma square root of n, which is 20. Okay, so plug this in our calculator. What do we get? So this is z. Let's see. We get 8 over 16 and then times square root of 20. So I got 2.236. So that's the same as 2.24. Okay, we keep 2 decimal places for the z values of the normal distribution. Well, we don't like greater than. Let's change to less than equal. Okay, so that is the CDF values of 2.24. Let's find our table. 2.24. Okay? Yeah, so 2.24, 0.9875. So let's come back. 0.9875. So the answer is 0.0125. Right? So that is the probability of a random sample of 20 people result in a sample mean greater than 108. So far, so good, everybody. So this is actually a good example because it can show us the difference between when we pick a random individual or when I pick a sample, a random sample. So compare this part A and part B. Yeah. All right, let's continue. Example 3. Suppose that the prices of women athletic shoes have a mean of 75.15 and a standard deviation of 17.89. What is the probability that the mean price of a random sample of 50 pairs of women's athletic shoes will differ from the mean by less than $5? Okay, let's identify the numbers. Okay, so here, all right, so we have, this is the mean, mu, standard deviation, sigma. Sometimes the problem might give you variance. Then you know to find the standard deviation, you need to take the square root of the variance. And then the mean price sample, so this is n. Okay, so we're looking for find the probability, the mean price. The mean price means the sample mean. Yeah, mean price of the sample, so sample mean x bar. Okay, sample mean x bar. Okay, so find the probability x bar will differ from the mean, population mean by less than $5. Okay, so this is what is looking for. Okay, so when we are given the sample mean, we know that by law of large number. Okay, the standardized sample mean sigma over square root of n, approximately normal. So approximately by the standard normal distribution. Okay, so let's try to convert this to z. Okay, what can we do here? You can see in order to get z, we have the top. We also need the bottom. So let's divide it by sigma over square root of n. Okay, you realize actually the sigma and the square root of n, they are positive. So this is the same as saying x bar minus mu over sigma over square root of n. So this is the same as the absolute value of z. So this is the absolute value of z less than 5 sigma 17.89 over square root of n, which is 50. Okay, so plug this in our calculator. So 5 divided by 17.89 times square root of 50. So we have 1.976. That's the same as 1.98, right? We round up. Okay, what does that mean? Well, it means z is bounded between 1.98 and negative 1.98. Alright, so that's the CDF values of 1.98 minus the CDF values for negative 1.98. Okay, so let's find those numbers in our table. 1.98, so 0.9761. Okay. And phi of negative 1.98. Negative last page. Negative 1.98 8. So 0.0239. Okay, so let's plot this in our calculator. So 0.9761 minus 0.0239. So our answer is 0.9522. So far, so good. So that's the probability of the mean price differ from the mean by less than $5. So you can see in this process, we didn't use the mean, right? Because we're looking for the difference between the sample mean and the population mean. Okay, so we didn't need to use the values of the mean. Okay, so that's example 7. All right, so giving you a sample, and when the problem asks you to find the probability, such as the sample mean is within some range, you're going to use the law of large number, okay? And then you can convert it to the standardized sample mean, which is x bar minus mu over sigma over square root of n. And then this guy is approximately by the standard normal distribution, okay? All right, so in this session, we learned 2 important theorems, the law of large number and the central limit theorem. I want to show you, actually, those 2 theorems cover different convergence. Okay, so here are the 2 convergence. Convergence in probability. And the second convergence is the convergence in distribution. What is convergence in probability? So we denote it by, convergence in probability. So we put a little p on top of the arrow. Okay, so suppose we have the sequence x of n, and we say the sequence converges to x in probability, even only if the probability of the difference of them less than sigma goes to 1 when n goes to infinity. What does that mean? Well, you know that because the x and xn are random variables, so xn minus x is also a random variable, right? Because it's a random variable, then we can draw the picture. So let me draw a better picture. Okay, so it means, so let's say this is the random variable xn minus x. Okay, and 0 is in the middle. And here, this is epsilon, this is minus epsilon. So this theorem tells us that the probability of the random variable lie in that range. So the probability of this green area, so this area goes to 1. Okay, so for example, if I want to draw a picture, okay, so if the n increase, what does that mean? You have smaller values, and here you have okay, let me draw it better. You have it more narrowed down here. Okay, so you can see when the n increase, you're gonna have more narrow down. The area is gonna be getting closer to the center 0. Okay, so this is convergence in probability. For example, in our law of large numbers, we have the xi's are IID data. So they're independent and identically distributed with mean mu, and then the sample mean is this. Then we have the sample mean converges the population mean in probability. Okay, so that's why we had the probability of the sample mean minus population mean less than epsilon goes to 1 when n goes to infinity. So this is convergence in probability. Okay, so sample mean is approximately so sample mean approximate the population mean. Okay, that's the first convergence. How about the second convergence? Well, the second convergence, we have the convergence in distribution. Okay, so suppose let x sub n be a sequence of random variables. So convergence in distribution means we have pointwise convergence in this cumulative distribution function. Okay, so suppose f sub n are the CDF values for x sub n respectively, and capital F of x is the CDF of x. The convergence, so we convergence pointwise means for h of x. Okay, the CDF of x sub n is going to be closer to the CDF of the x. Okay, if we want to draw the picture of it, so let's look at the CDF. Let me see. Okay. So suppose we have the CDF. Okay, so let's say well, CDF looks like, okay, so let's say CDF of x is like f of x. It looks like that. Okay, it goes to 0 on the left, it goes to 1 on the right. Okay, and what does that mean by saying we have a sequence Sn, the CDF converge to that pointwise? So, okay, so the picture is, could be like that. Okay, could be like that. So you can see, for each x values, when the sequence increase, then you can see the CDF of that sequence is getting closer to the CDF values of x. But however, so we guarantee convergence at each point, but the speed when they converge could be different. Maybe here it converges slower, and here it converges faster. So we cannot we don't know how the speed. We only know like at each point, this function's f sub n converge to f of x, but we don't know like whether they converge at the same speed. Okay, so this is pointwise convergence. Okay, so convergence in distribution. Our example is the central limit theorem. Okay, if we have a IID data with mean mu and variance sigma square, and the standardized sample mean is gonna be it's gonna converge to the standard normal distribution in distribution. So this is convergence in distribution, i.e. the CDF of the z's. Okay, when n goes infinity, it converges to the CDF of the standard normal distribution. Okay, so here are the two different convergence in this session. Okay, so don't forget, if you have questions, feel free to email me or ask me during the online office hours. Bye!